Hello, welcome to my channel Mathematics with Sachin Dikshit. This is fifth lecture on dynamic programming. In previous lecture, we solved some models on dynamic programming, general examples on that model. In this lecture, we also solve another model and one more example corresponding to that model. This model corresponds to additively separable return function. Means objective function is additively separable and single multiplicative constant means constant is multiplicative. We take one example of this model. Use Bellman principle of optimality to solve minimize z is equals to y1 plus y2 plus y3 up to yn subject to y1 into y2 into y3 up to yn is equals to d. All yi's are greater than or is equals to 0 for all I. Here objective function or return function is z is equals to y1 plus y2 plus y3 up to yn and one single multiplicative constant is y1, y2, y3 up to yn is equals to d. That means we have to factorize the quantity d into n parts such that sum of these n parts will be minimum. Solve this problem. Solution. Again the procedure is as previous. That means we have to start with n is equals to 1, n is equals to 2, n is equals to 3, then generalize it into n is equals to n, then the result in n is equals to n will be proved by using induction process. The procedure is as previous is previously examples which we have to solve. The same procedure will be applied again here. The difference between this example and previous is objective function and constants will be of different kinds. We start with the solution. Let f and d denote the minimum attainable sum y1 plus y2 plus y3 up to yn, where the quantity d is factorized into n parts, that is y1, y2, y3 up to yn is equals to d. We consider the first case where d can be factorized into only one parts. That means f1 of d is minimum of y1 and that value is nothing but d only. That means f1 of d is equals to d. Equation number 1. Consider the second case. For n is equals to 2, f2 of d is equals to minimum of y1 plus y2. Here the quantity d can be factorized into two parts. Let y1 be the first part. We take it as p. Then obviously the second part of d is nothing but d by p, as since y1 into y2 is equals to d, put y1 is equals to p, we get p y2 is equals to d, implies that y2 is equals to d by p. Therefore the two parts of this quantity d will be one is p and other is d by p. We put these values of y1 and y2 in this expression. We get f2 of d is equals to minimum over p of p plus d by p. This can more precisely write as f2 of p is equals to minimum over 0 less than p less than d of p plus f1 of d by p. Since f1 of d is equals to d, therefore f1 of d by p means d by p. Equation number 2. Let p plus f1 of d by p is minimized by using calculus as follows. Let y is equals to p plus f1 of d by p, that is y is equals to p plus d by p, as f1 of d is equals to d. F1 implies that f1 of d by p is d by p. For minima, dy by dp is equals to 0. We have to find out its derivative. Derivative of p with respect to p is 1, and derivative of d by p, here d is constant as it is, and derivative of 1 upon p is minus 1 upon p square is equals to 0. This plus multiple of this minus, it gives minus 1 minus d by p square is equals to 0. Now we transfer this negative term from LHS to RHS. We get 1 is equals to d by p square. Then cross multiply by p square, we get p square is equals to d. Obviously p is equals to d raised to half. Therefore, the first part y1 is nothing but p, which is equals to d raised to half, and y2 is equals to d by p. Put p is equals to d raised to half. We get y2 is equals to d divided by d raised to half. D divided by d raised to half is nothing but d raised to half. And y mean is equals to p plus d by p at p is equals to d raised to half. That means we have to put here p is equals to d raised to half. We get y mean is equals to d raised to half plus d divided by d raised to half. D raised to half, first d raised to half as it is, plus d divided by d raised to half means d raised to half, as we know one result as a raised to m divided by a raised to n is equals to a raised to m minus n. Here d raised to 1, here d raised to half, therefore it is d raised to 1 minus half. 1 minus half is half. Hence d raised to half plus d raised to half. D raised to half plus d raised to half, it means 2 times of d raised to half. That will be the minimum value of y when n is equals to 2. Thus y is minimum when y1 is equals to d raised to half, y2 is equals to d raised to half. They must be equal and its value will be d raised to half. Hence the optimal policy for n is equals to 2 is the two parts y1 and y2 both are equal, and that value will be d raised to half, and corresponding objective function gives f2 of d is equals to 2 times of d raised to half. Total equation number 3. Now come to the case for n is equals to 3. That means the quantity d is factorized into 3 parts. Let y1 is equals to p. That means first part we take as p, and obviously remaining part will be d by p, and that d by p part can be further factorized into 2 parts. Therefore, by Bellman's principle of optimality, we can write f3 of d is equals to minimum over 0 less than p less than d of p plus f2 of d by p. Equation number 4. Since f2 of d is equals to 2 times d raised to half, implies that f2 of d by p is equals to 2 times d by p raised to half. Now we put this value of f2 of d by p in this equation number 4. Therefore equation 4 becomes f3 of d is equals to minimum over 0 less than p less than d of p plus 2 times of d by p raised to half. Now again we minimize p plus 2 times of d by p raised to half by using simple calculus as follows. Let y is equals to p plus 2 times of d by p raised to half. For minima, dy by dp is equals to 0. We have derivative of p with respect to p is 1 plus 2 times as it is. Now we have to find out derivative of this term, d by p raised to half. It will be 1 by 2 as it is, d by p raised to 1 by 2 minus 1 into derivative of d by p. D as it is, and derivative of 1 upon p is minus 1 upon p square. Therefore this expression will be exist. Now this 1 by 2 and this 2 will get cancelled out. 1 by 2 minus 1 means it is half. That means the expression is 1 plus d by p raised to minus half minus d by p square is equals to 0. That implies 1 plus. Now collect the powers of d in the numerator and collect the powers of p in the denominator. In the numerator, in first term d raised to minus half, and in second term it will be d raised to 1. Hence we collect that power and we get d raised to minus half plus 1. In the numerator, in the denominator, p raised to minus 1 by 2, and here p raised to 2, it means p raised to 2 minus 1 by 2, and this minus into this plus gives minus sign. Simplify this. Minus half plus 1 gives half, and 2 minus 3 by 2 gives 3 by 2 is equals to 0. Now multiply this p raised to 3 by 2 on both sides. We get p raised to 3 by 2 minus d raised to half is equals to 0. Now we transfer this negative term from LHS to RHS. We get p raised to 3 by 2 is equals to d raised to 1 by 2. Taking square on both sides, we get p cube is equals to d. That means p is equals to d raised to 1/3, and y mean is equals to p plus 2 into d by p raised to half at p is equals to 1. P is equals to d raised to 1 by 3. That means we have to put in this expression p is equals to d raised to 1/3. We get y minimum is equals to d raised to 1/3 plus 2 times of d divided by d raised to 1/3 whole bracket raised to 1 by 2. That means just we replace p by d raised to 1/3, and now we have to simplify this. For that, first term as it is d raised to 1/3 plus 2 as it is. Here d raised to 1, here it is d raised to 3 by 2. One another law, a raised to m divided by a raised to n implies that a raised to m minus n. That we have to apply here. In the numerator here d raised to 1, in the denominator d raised to 1/3. Hence it will be d raised to 1 minus 1/3, that is 2/3. Hence it is d raised to 2/3 whole bracket raised to half. Now d raised to 2/3 whole bracket raised to half means this 2 gets cancelled out, because another law is exist, a raised to m raised to n is equals to a raised to mn. Means in that case 2 gets cancelled out and it will be 1 by 3. That means y mean is equals to d raised to 1/3 plus 2 times of d raised to 1/3. Here 2 times of d raised to 1/3, here 1 times of d raised to 1/3. Total it will be 3 times of d raised to 1/3. That will be the minimum value of y when n is equals to 3. Thus y is minimum when y1 is equals to d raised to 1/3 and y2 is equals to y3 is equals to d raised to 1/3. Means all the three parts are equal and their value will be d raised to 1/3. Hence optimal policy for n is equals to 3 is y1, y2, y3, they are all equal and its value will be d raised to 1/3 each, and therefore 3 f3 of d is equals to 3 times of d raised to 1/3. Equation number 5. Proceeding in this way, we will get the optimum policy for n is equals to n as follows. y1, y2, y3 is equals to, again these n values must be equal and each value is of d raised to 1 by n, and therefore minimum value of return function fn of d is n times of d raised to 1 by n. This is general result for n is equals to n. Now we have to prove this result in equation 6 by using induction process. The result in equation 6 can be proved by using induction process as follows. Clearly, equation 6 is true for n is equals to 1, which is already proved here. Let the equation 6 be true for n is equals to m. That is y1, y2, y3 up to ym. All these are the m parts of d, and these parts are equal and each part is of value d raised to 1 by m, and therefore fm of d is equals to m times d raised to 1 by m. Equation number 7. That means we have to take the optimal policy when n is equals to m. Now we have to show that equation 6 is true for n is equals to m plus 1. We have by Bellman principle of optimality, fm plus 1 of d is equals to minimum over 0 less than p less than d of p plus fm of d by p. Equation number 8. Since fm of d is equals to m times d raised to 1 by m, that implies fm of d by p is equals to m times d by p raised to 1 upon m. Hence equation 8 can be written as fm plus 1 of d is equals to minimum over 0 less than p less than d of p plus m times of d by p raised to 1 upon m. Raised to 1 upon m. Let p plus m times of d by p raised to 1 upon m is minimized by using calculus as follows. Let y is equals to p plus m times of d by p raised to 1 upon m. For minima dy by dp is equals to 0, we have to find out its derivative. Derivative of p with respect to p is 1. This m as it is. Now we have to find out derivative of d by p raised to 1 upon m. For that 1 upon m as 1 upon derivative of this term is 1 upon m into d by p raised to 1 upon m minus 1 into this derivative of d by p is nothing but minus d upon p square equal to 0. Now we have to simplify. This gets cancelled out and here cross multiply by m. We get 1 plus d by p raised to m minus 1 divided by m into minus of d by p square is equals to 0. Now in the next step we have to collect the powers of d in the numerator and powers of p in the denominator. In that case we get 1 plus minus of d raised to 1 minus m divided by m plus 1, and in the denominator p raised to 2 plus 1 minus m divided by m equal to 0. Now we have to simplify this term. This cross multiply, we get 1 plus of minus into d raised to 1 minus m plus m divided by m, and in the denominator p raised to twice m, cross multiply by this m, we get twice m minus twice m plus 1 minus m divided by m equal to 0. Simplify this. 1 plus minus sign as it is, d raised to 1 upon m. This gets cancelled out. Remaining part is 1 upon m. And in the denominator, 2m minus m gives m. Therefore, it will be p raised to m plus 1 divided by m equal to 0. Now, this minus into plus gives minus sign. Therefore, 1 minus d raised to 1 upon m divided by p raised to m plus 1 divided by m is equals to 0. Then cross multiply this p raised to m plus 1 divided by m. We get p raised to m plus 1 divided by m minus d raised to 1 upon m is equals to 0. Now this transfer d raised to 1 upon m from LHS to RHS. We get this expression p raised to m plus 1 divided by m is equals to d raised to 1 upon m. Taking mth power on both sides, we get p raised to m plus 1 is equals to d only. That means p is equals to d raised to 1 upon m plus 1. And minimum value of y is equals to p plus m into d by p raised to 1 upon m at p is equals to d raised to 1 upon m plus 1. We put here p is equals to d raised to 1 upon m. We get y mean is equals to d raised to 1 upon m plus 1 plus m times of d divided by d raised to 1 divided by m plus 1 whole bracket raised to 1 upon m. Now we have to simplify this. Y mean is equals to d raised to 1 upon m plus 1 as it is plus m as it is into bracket. Again base is the same, powers the terms in division, therefore it will be, we have to subtract these powers and we get d raised to 1 minus 1 divided by m plus 1 whole bracket raised to 1 upon m. Cross multiply here, we get y mean is equals to d raised to 1 upon m plus 1 plus m into bracket d raised to m plus 1 minus 1 divided by m plus 1 whole bracket raised to 1 upon m. This plus 1 minus 1 gets cancelled out and we get y mean is equals to d raised to 1 upon m plus 1 plus m times of m d raised to m divided by m plus 1 whole bracket raised to m. Now we multiply this, we get d raised to y mean is equals to d raised to 1 upon m plus 1 plus m as it is into d raised to 1 upon m plus 1. This m gets cancelled out. This is m times, this is 1 times. It is nothing but y mean is equals to m plus 1 d raised to 1 upon m plus 1. Thus y is minimum when y1 is equals to y2 is equals to ym is equals to ym plus 1 is equals to d raised to 1 upon m plus 1. It means all the parts will be equal and each will have a value d raised to 1 upon m plus 1. Thus equation 6 be true for n is equals to m plus 1. That is y1, y2, y3, ym plus 1 is equals to d raised to 1 upon m plus 1. That means all these m plus 1 parts each will have a value of d raised to 1 upon m plus 1. And therefore return function f of m plus 1 of d is equals to m plus 1 of d raised to 1 upon m plus 1. Equation number 9. Hence, by principle of mathematical induction, the result in equation 6 is true for all n. Hence, the optimal policy of given problem is given by equation 6 as y1, y2, y3 up to yn. These are the n parts of d. Each part is of value d raised to 1 upon n, and the return function f n of d is equals to n times of d raised to 1 upon n. Equation number 6. Hence the result. That is one another model of dynamic programming, where additively separable return function, that is objective function is additively separable, and constants is single multiplicative constant. It's the example. These are the reference books for this corresponding term, corresponding video. Thank you for watching this video.